So let's write down the definition of an abstract group. A group G is really three things. It's a set G together with a binary operation so this is a function from G cross G to G. Just to be neutral, we'll denote this right now by a star. So be in different contexts is denoted by different things. And a distinguished element E satisfying the following three things. So really a group is a triple: the set, the operation, and the special element. But we don't say the triple all the time. We'll just write G for the group. The other two things will be taken as understood. But to give someone a group, you have to give him the set, describe the operation, prescribe the special element. And what are these three properties? They are A star B star C done in two different ways gives you the same thing for all A, B, C, and G. When I write A star B, I will sometimes call it A times B. Too used to that notation. A times E is A, and same is E times A. So when you multiply by this identity, you get the same thing back for all A and G. And then finally, for all A and G, there exists an element. Let's call it B, such that A times B is B times A is identity. This element, we will see that in any group, if you assume that it exists, then there can only be one such thing. So usually it's denoted by A inverse, and it's called the inverse of A. So you get there is an element A inverse such that A times A inverse is A inverse times A is identity. This is called the group law of G. And this is called the identity element of G. And these three axioms also have names. This one is called associativity. This one is called the identity axiom. And this one is called the inverse axiom. So a group is any set, finite or infinite, together with this operation star and a special element E satisfying these three laws. We say that G is abelian if, or commutative, if, so that's the new word, if A times B is B times A for all A, B in G. Okay. This star, this group law sometimes have alternate notations, so this is important. The group law is sometimes denoted. In different examples you use different notation because these are things that actually show up in different branches of mathematics, and these already have some notation set to them. The group law is sometimes denoted by a dot. So you write A comma B going to, instead of writing A star B, you write A times B, or just AB, or sometimes A circle B, or sometimes even A plus B, but this will reserve when G is abelian only. We'll use this last one only when G is abelian. Only when G is abelian. I mean, if G is abelian, we will not necessarily use it, but we'll use it only in cases where it is abelian. Okay. So now for some examples. So if you take, basically the way they arise in mathematics is, this first is sort of a meta example, set of symmetries of mathematical objects. Objects often give examples of groups. And by what sort of object? We saw symmetries of the square form a group. That was our first example. Could take symmetries of the cube. Any geometric shape. If you take a wiggly amoeba shape, then there is no symmetry that preserves it. So the group is just trivial, just a group which has one thing, the identity. That's a silly group. This group we saw is rather interesting. It has 8 elements. If you want to think about the symmetries of this, by symmetry I mean reflections and rotations, then you will find that there are 48, I believe. And if you just take rotations, then you'll find 24. Or you could take any n-gon, for example. The symmetries of a hexagon would have 2 times 6, 12 elements. So this one was called the dihedral group D4. This one is called the dihedral group D6. Okay. So similarly, you could take any n-gon, like a pentagon or a heptagon or something, and take its symmetries. The symmetries of a regular pentagon would have 10 elements, etc. You could take more exotic figures like a icosahedron, the 20-faced die, which you may have seen. It looks like this, kind of looks like a diamond. And then, so you see 10 faces in front, and then there are 10 faces behind, kind of a diamond-looking shape. Each face is a equilateral triangle. If you just take the rotational symmetries of this, you get 60 rotational symmetries. Etc., etc. You could take higher dimensional shapes and their symmetries. You could take, but these are all finite set of symmetries. You could take, on the other hand, maybe very symmetrical shapes like the circle. That's also a shape in the plane. It's a perfect circle. Then the symmetries of this shape is infinite. Because you could basically rotate a circle by any angle. If you give me any number between 0 and 2 pi, I can rotate the circle by that amount, call that r theta. Then r theta is a rotation by angle theta, which takes the circle C to itself. So the symmetries of C, just rotational symmetries, let's say, is given by all these r thetas, where theta could be any angle between 0 and 2 pi. Well, 2 pi rotation is back to identity, so I don't count that. Yeah. And then the group law here is rather simple. When you apply a rotation by theta and then apply a rotation by alpha, you get r of alpha plus theta, but you have to read this mod 2 pi, meaning if this happens to be, like if you take 270 degree and 270 degree, then you get 180 degree, because 270 plus 270 gives you 360 plus 180. And this 360 goes away because it's 2 pi, so it's just 180. That's the group law. So alpha plus theta, I'll say mod 2 pi. Yeah. So the remainder after you take away enough 2 pi's. That's basically the group law, but it's now an infinite group. But then you could take other kind of mathematical structures, more exotic things like a surface, the surface of a donut, or higher dimensional cousins of them, and take their symmetries. These things are sometimes given by equations, this sort of surfaces and so on. So you could take symmetries of equations, meaning what? Meaning change of variables of these equations which leave the equations unchanged. All these different sources give you symmetries of mathematical objects. If you're a graph theorist, then you study graphs, and you can look at transformations of the graph that takes vertices to vertices and edges to edges. So in any branch of mathematics, when you have symmetry available, it actually helps the study of the object. And moreover, in different branches of mathematics, you see that similar symmetries show up. So this we should write down, I suppose. Similar within quotes. If you know what this word means, isomorphic groups of show up in different branches, like in geometry and number theory, let's say, mathematics. And when this happens, this gives you a bridge between these branches. And that's how group theory helps, because you see sort of that the same group in abstraction shows up in two different places. That indicates that these two different branches, these two different areas of mathematics, these two different objects of mathematics maybe has some link. And that's sort of how this subject often gets used in mathematics. So these are some rather impressionistic examples. We'll write down more concrete examples in a bit.